Oh,
That was the start of the. All right, we're being rude to Don. Sorry, Don.
No, I'm good. I'll start whenever you're ready.
Go.
Okay, you guys ready?
you have the slides up.
I do. Okay.
Do we have a IO?
Do you have a
Do
what?
we have a stream? I don't
I assume you do.
see Brad. There's Brad's head. And he looks like he's still tinkering.
What? You can proceed when ready.
Okay, cool. Go ahead, Don.
Okay, so I'm Don Golding. I'm going to give a little talk about the project I've been working on for quite a while. The Core 1 boards, and there's one right there. I gave a talk at an online virtual conference called Summit of Things, and about AI and IoT just recently. Come on. So currently I'm a senior staff engineer at a little company called Next Stage, and I'm designing. I had an idea for a product in the space business, and this company's decided to let me go ahead and develop this product for them. You know, I'm just an engineer, but they'll own the product. But I'm very happy to be working on it because it's not something, you know, it'd take a lot of money to get started, try to do something like that. So I'm currently designing a development system for space avionics that will consist of Earth COTS that simulates the space hardware, the space board, which is basically a 4-inch square. It's 100 millimeters on a side. It's called a 1U in space jargon. And I'll have a version that uses Earth COTS, and then another version using rad hard components. I also founded a company called Space Tech. I had that for about 5 years, making some medical imaging type systems, electronic stuff, mostly video. I was a founder of Angeles Research Corp, and for about 12 years, I had that company, a couple of employees, and we did a lot of intelligent robots. I developed a robot called Whiskers that was sold into STEM. About 2,000 robots were sold. Every year, my Whiskers robot was teaching kids in junior high and high school how to program intelligent robots. A couple of the bigger projects I worked on this Lockheed Martin Mule, which would really ruin your day if you saw this sucker coming down the street. Also worked on the Redwire Archinaut 1 mission. They call it OSAM-2, which is on orbit, service, and manufacturing. This is a NASA project, and I did that for Redwire. I designed the rad hard computer for this one. And here's a bunch of robots that I built at Angeles Research. And I actually built the first man-packable robot before iRobot's PackBot came out. I hooked up with Major John Blitch, who had $80,000 in funding with the AI Army AI lab. And I developed the very first proof of concept prototype for that program. Where could we use this technology that I'm working on? Basically everything. So it'd be a great motor controller for any sort of robot, whether it's walking, crawling, flying, CNC machines. Maybe Mitch could use it. And my Christmas present is going to be that digital barbecue smoker over there. So my fiance is listening. She needs to sign up and get that. So in order to get hooked up with the AI community, which I, strongly interested in AI and robotics, I started an AI and robotics group on LinkedIn. you'll notice we're up to 2,353 members, upper right. And if you go on the group and you click show all, I think you'd be amazed at the quality of people in the group. And there are CTOs, CEOs, programmers, project managers in the areas of space robotics, large language models, and pretty much the whole 9 yards of AI. I've only started this group back in May, so it's really grown quite fast. At the bottom there, you have the address, or just go on LinkedIn and search for AI and robotics, and please join. I also created a Facebook page. Now, this is probably 8 or 9 months ago. We have like 321 members, but they're definitely a different group. There's members, you know, from the 4th 2020 group. There's some members from SVFig, and it's kind of attracting more readers than anything else. But we do talk about a lot of AI stuff. And on both these groups, I'll be talking about the Core 1, you know, once I get it fully operational, the board. So now I'm going to talk about the Core 1 a little bit. So I want to use this video to send out to people. So I'm going to go over why I chose Forth in the first place. So Forth was invented in 1963 by Charles Moore. Forth uses a chatbot interface since the very beginning. I think it's pretty interesting that it took 60 years for computer science to come up to Chuck's invention there. And of course, the thing that's really important about Forth, as far as using it as an intelligent and extensible chat box, is it has a built-in outer interpreter. It promotes simple testing and debugging. It has a simple incremental compiler. If you compare the Forth compiler, which is a few lines of code, versus the C compiler, which probably a team of 50 built and is a huge, complicated beast, you'd be amazed at the difference. And the interesting thing about C and Forth is they both run about the same on a typical processor. So there isn't a huge speed benefit for C. Forth is really a virtual machine, and it's very easy to implement on a chip. I don't know any other language. There's been a couple of chips, I think maybe Lisp, and I forget the other one, about 20 years ago, but there's been a couple of attempts to put a language on a chip, and Chuck did this in 1980, in the 80s with the, what was it, the NC 4000, I think was the first one. I think he had one before then. But anyway, Chuck's been building Forth virtual machines in silicon. He's got, you know, half a dozen different versions over the last 30 years. So it's very easy to implement Forth in silicon. And my focus is FPGAs. Forth is also a meta language, and it's very easy to implement or steal things from other languages. If you like something in another language, you can turn around and you could write, you can write compiler type words in Forth to implement those things in other languages. Like, for example, struct in C. It's easy to write struct in C. It's easy to create string manipulation words. Dr. Ting gave us some quite a few talks when he was doing some genetic kind of research. You know, like when we first got the disease, you know, the Delta and all that other stuff, COVID. And one of the things I remember him saying, that he was using Python, but he rewrote it in C and it ran 60 times faster. So why not use C? It's not interactive. unless you use a derivative like Java or Python. It's a very complex compiler, requires a powerful computer just to compile your software. You must compile the entire application if you change one line of code. You don't have to do that in Forth. You can actually create what's called a deferred word if you want. You can literally replace a function inside Forth after the entire application is compiled. Then in C, you have to JTAG the binary file into the CPU. You need a lot more memory to run it and a lot more processing power. Reprogramming on the same machine requires an OS like Linux or Windows. Forth and hardware. Here's all of Chuck's machines. I put the FPGA in there because to me that's the next gen. That's what I'm working on is Forth on FPGAs. But Forth is a virtual machine. It's more than a language. It's really the design of an ideal computer, a very simple, powerful, ideal hardware computer. And like I said, Chuck's chips, the NC4000, the Shaboom, RTX 2000, and Dr. Ting's F21, and there's many others. There's, the J1, what is Dr. Ting's E16? But anyway, that's the F21, I guess. Anyway, there's Green Array's 144 multi-core Forth processor chip. And if you want to look at some of the chips, go to Ultras Technology down there /chips. So general purpose computers versus Core 1. On a typical software program, only a small fraction of the available CPU opcodes are actually used. So Intel creates a chip and they say, what opcodes do I need? Well, I need to do debugging. I need to do this. I need to support virtualization. I need to support all this stuff. And the typical application literally only uses 5 to 10% of the CPU's instruction set. The Core 1, you can actually comment out instructions that you're not using in the system Verilog code, and you can get your optimal utilization up to 95%. And also the typical chips like from Intel are very high power consumption. They're very complex, low efficiency, and high cost. Core 1 FPGA benefits. So you just by changing one parameter, you can go from 32 bits to 64 to 128. You can go 57 bits. I mean, it doesn't matter the way we wrote the code. The outer interpreter is on chip, and now this is new to Forth chips. We put the outer interpreter and incremental compiler on chip, written in system Verilog. It's built on the Forth virtual machine. You send source code through the terminal interface, which is a simple RS-232 cable running on 115 kbaud, and your source code will download inside the chip itself. It will be parsed and compile, and then you can interactively execute and test your application. So you don't need any external development tools. I did on the board, I put a PS2 keyboard interface. We also have an ESP16 that has a Bluetooth interface, so you could literally use your cell phone or some sort of Bluetooth device to talk to it as well. My goal in the future is to build a very high level natural language on top of Forth. So it's literally like you're talking to the Star Trek computer. So some of the features we have, you can microcode Forth programs and words in boot ROM. The boot ROM can exist inside the chip, or It could be the external flash that I put on the board, either one. The Core 1 opcodes can be very complex. So in the 1990s, before 1980, we had computers that were used complex instruction set, or CISC. And then we wanted to run faster, and so we decided and have more flexibility. So we went to RISC, which is reduced instruction set in the 90s, and we pretty much stayed on that for the most part. So the processors do a very simple things like move memory location address, the contents of the address into register, A. Move another memory location into B, then call a routine that will add the two together and put it on the stack or put it in another register. Whereas the Core 1, you can literally write very high level things like, let's say you want a SHA-256 opcode. You can write that in System Verilog, and it could take 50 clock cycles, and it doesn't matter because the way we implemented the internal, we call it the inner interpreter in the fourth world, and it's basically the execution engine. It stalls until the opcode is complete. So in your System Verilog, you have a busy flag, and you set the busy flag to true, entering your code, and then you write whatever code you want, and then you set it to false when you exit the code, and the internal execution engine will stall and not get the next opcode or word to execute until that's completed. And what's nice about that is with FPGAs, they teach you, to build things in a digital fashion, and everyone wants to do things in a clock cycle. And so you have to simulate your code in a simulator like Model Sim, and if it doesn't execute fast enough, then you may get false information. And none of that is a problem because we have the busy flag. It's real simple. And all the words, we are using combinational logic rather than rather than using clock logic. So because of that, your opcode actually will execute at the speed of silicon because it's basically the propagation delay through the gates and the lookup tables until it gets to the answer at the end. So it's kind of like what the GA144 does. That's combinational logic. The computer grows as the FPGA technology grows. So, as you get bigger and faster FPGAs, you just have more, silicon to work with. You could go to 1,000-bit with whatever you want. You can network multiple engines together over an internal network on the chip. So, for example, with an 85K LUT chip, you could probably put 40 32-bit Core 1s on it, similar to like what a GA144 does. Although I don't think that's the most efficient way to use the system. I'll get into that a little bit later. You can store source code in Flash or on the SD card. You can compile on the fly as needed if you want. You can take a snapshot of the SRAM and you can store it in Flash or the SD card, and you could recall that. And which is an interesting concept. Think like you're using an Excel spreadsheet and you have a snapshot for that, and you switch to editing a document, you have a different snapshot for that. So all of the different memory, the memory variables are all stored. And so you start exactly where you left off. How would you like a computer that was instant on and came up where you left off? So the Core 1 development goals, which is why I started the AI groups. I want to develop a vast open source user community in AI. And so imagine a GitHub where we're all creating opcodes and application code and sharing it amongst the community. Extend the system for an intelligent chat box user interface. In other words, we can make the interface, the language, we can build on top of Forth and make a really natural language to program in, almost English. And we don't even have to use RPN. Okay, we don't have to use RPN. We can actually parse the code and we can build it and convert it to RPN for execution, for example. So users can quickly and easily add their own words to the system. I've done some research into these large language models. You can go out and download the Llama, which is Meta's data set for their chatbot. Their big one is 70 billion parameters, but the 7 billion parameter data set will actually fit into flash memory on the board. It's 33 megabytes in size. Now, that's basically consists of all the weights and stuff like that that loads into the PyTorch model. So that's not a complete system, but what I'm saying is we can load the data on the board. So if we could create the model, the inference engine to use this data set, we could run it on the board. And I would love to get some researchers maybe in one of these, in the robotics and AI group to work on that. Okay. So in a nutshell, you can create your own complex opcodes and system Verilog. System Verilog is almost everybody probably really knows it because it's C syntax. There's some gotchas there, but one of the things I plan on doing is once the boards are running is I'll start putting on courses online and teaching everyone how to use it. Like I said, sharing opcodes on GitHub. Each opcode runs at the speed of silicon, 200 megahertz. And each system Verilog process also runs that fast. And you can have thousands of parallel processes on an FPGA. So my board can handle up to an 85K LUT, 85,000 LUT FPGA, which is a huge amount. For example, the basic Forth engine is 2,600 LUTs. And that's a true 32-bit Forth. So there's some, there's some words that we need. That's not the full, like it's not the F83 instruction set yet, word set, but it's the basics of Forth. It's compiling. We need to implement crate does and all that. So the more powerful way to use the system is to really use system Verilog in conjunction with with Forth. So when you write things in system Verilog, they run in parallel at 200 megahertz. So think of a UART. So that UART you write in system Verilog, it's completely independent, and you can basically have a shared register for the Forth computer to talk to the UART. And if you have a motor controller or you have motor encoders that are inputs, you can do the same thing. You create a shared variable, a shared register, and you read and write. The Forth computer reads and writes to these shared registers and controls these system Verilog parallel processes on the chip. So this would be a really awesome real-time system for embedded systems. So like I said, Forth plus System Verilog, a powerful combination. The user interface on the computer is on chip in Forth, which creates easy programming. It's a natural language processor interpreter, incremental compiler. It's the extensible high-level language, and this is the user interface. The chip processing in System Verilog, the code becomes a chip circuit, literally a circuit on the FPGA. All processes run in parallel, and it's massively parallel processing capable. So we're going to use Forth as the user interface, as I said, and think of System Verilog as the assembler of this system. Obviously, it's I'd rather read System Verilog code than assembler code any day. And also it's going to run faster because it's not just executing, it's creating circuits. So best way to use it is you program all device drivers in System Verilog. Like I said, all System Verilog processes run at 200 megahertz plus. They all run in parallel. And FPGAs can run thousands of parallel processes concurrently. Multitasking will be supported in the Forth machine. So here's a block diagram of what my board is. So inside the chip, you can see the Forth computer that has the incremental compiler, outer interpreter. It's a full Forth computer. It's not just a Forth processor like the other ones that came out previously. You might think about putting a core. So a Core 1 core is only the inner interpreter, and so you have to microcode a Core 1. So you can have dedicated boot ROM for each one of these Core 1s inside of the FPGA. So you could literally write a display controller, and so we have the top upper right Core 1 is managing the display. You might put one on the flash, and because that's basically managing long-term memory. And then you can also put one, say, on the SD card, and all these three cores run in parallel. So you could have the core that's running the SD card searching, through all of the files and data on the SD card while the display is running, while we're doing something else with the flash. The flash might be reloading the Forth computer with a different snapshot, or you could actually extend the dictionary into flash. And think about that, because you have 256 meg by 16 of flash. You can put a lot of code and data in there. Like I said, there's a PS2 keyboard. I have external SRAM for the Forth computer, and it was designed for cache for motherboards, and it's a 3 nanosecond access time. The FPGA has a propagation delay of about 2 nanoseconds. So basically, the external SRAM can run at the speed of silicon in the FPGA. So this Forth is going to really scream. Most primitive opcodes, swap drop, that sort of thing is going to be, one clock cycle at 200 megahertz, for example.
Break. Sorry to interrupt, Don. How much more do you have?
How much time do I have?
Minus 8 minutes, I think. So can you wrap up in 2 minutes?
I'll try to wrap it up.
All right, 2 minutes.
I'll wrap it up. Okay. What if you wanted to use C and you want to use the Forth? So here's an example how you do that. You can actually do it on my current board. What you do is you would allocate the, no, that's the next one. It'd be this one. You would allocate the SRAM to the RISC-V, and the Forth computer can use on-chip SRAM inside of the FPGA, as an example. So, you know, our model has been sequential, and, you know, let's get parallel, guys. It's time to get parallel. This is a side view of the board, how they stack up. The bottom board is a custom board, which I can, I'll design some, like a Whiskers 2 board, that sort of thing. So there's the board. I guess that's pretty much it for me. There's an example of a system Verilog. It's one line of code, and that's just to add the top of the stack and the second item. So it's one line of code. So that's how easy system Verilog is. This is an example of code that could create thousands of concurrent processes. So guess I'll leave it at that. Okay.
Okay, if anybody has any great questions of great immediacy, and all right. On that cheerful note, thank you, Don.
Hey, I do have a question.
Make it fast.
Is there any way that Don could maybe go through the last half of his stack at the end of today and do a better job of the last half? Because I think he did have some things that, and I'm part of his group, so I was really looking forward to hearing the whole presentation. And I'm sorry that, you know, he had so much good stuff that he had to say that he ran out of time. But maybe we could append his talk at the end.
It was a 20-minute talk that he ran 30 minutes on. So sorry to say we've got an agenda for today, and we try to stick to it. How about December? Does that suit you?
I was asking if we can add another 30-minute at the end for him.
Not going to do that. How about December?
Okay. Very great. Great.